make a joke really at all. If you
Oh,
can't,
oh,
if your society can't deal with comedians,
Dude, I stripped my whole profile on Facebook. I'm one of those people. I deleted myself from all the hidden databases that your name is stored in with all your address and all your work history and everything like that. I scrubbed myself using Zorro because I've been applying. Are we streaming?
yeah, we are. Do you want me to stop?
Okay, never mind.
Sorry. It just started
your
right
mom
now.
started again.
I could stop it. It's not a big
Nah,
deal.
it's fine. It's just like this cancel culture stuff is very interesting.
Don't say
time.
interesting. It's terrible. It's terrible.
I think you should restart the stream.
They're trying to cancel like
I
Howard
know, right?
Stern.
Don't worry, man. I'll edit. I'll go through the streams in general and just not even for the sake of the content of what we're talking about, but more because I would like to reduce them to really important chunks of information at some point. But this for live streams, so I feel like whatever, like say whatever you want. It's fine. I just have to make sure the restrictions are not necessarily made for kids, At first I was putting it made for kids, but we'll say the published ones will be made for kids. These ones are just drinking beer on it. It's like,
That's how you get more viewers anyway.
I got a question for you guys before you do anything, Michael. So this beer here, I know it probably the
From
words
Scranton, Pennsylvania?
No. Read it carefully. I thought it said Scranton also. Are the words backwards for you? They're backwards for you guys.
Scantron.
Do you know what that is? Do you know what that is? Do you know what
No.
You don't know what a Scantron is? Oh, okay, so that's...
Scantron. Yeah, you take tests.
No, I don't.
Yeah. I was just curious. So this...
Wait, what is it?
Oh, you don't know. So this brew...
You don't know what a Scantron is?
No.
Yeah. So, let me just set the stage for you real quick. So this brewery is a really cool brewery. You go in there and they're just banging like Wu-Tang Clan, Beastie Boys, like all the stuff, like rap, mostly rap music, but all the stuff that I grew up with, like Q-Tip and Tribe Called Quest, like that kind of stuff, all the time. And yeah, it's like not exactly underground, but that scene and stuff like that. So they're obviously like my age, the people who run this brewery or whatever.
Yeah.
And a Scantron is totally an example of like. I actually asked my wife. I was like, "Does Colby even know what a Scantron is?" And now that my brother doesn't know what a Scantron is, are you googling it, Shane, right now?
Yeah. Bro, I don't know what this is, man.
Oh my God, you were like so much younger than.
That's what I'm saying, man. It's like a total ageism type of thing, right? It totally ages you. I thought they would still be out there, though. I mean, didn't they? Probably when you took the SATs, Shane, it was probably something like a Scantron type of machine.
What do you mean took? Like I just took the test and gave it to someone. What do you mean? I don't know.
What do you mean you gave? Did you fill in bubbles?
Yeah.
That's
that's
Scantron
what this is.
Scantron is a separate piece of paper that used to.
Yeah, it was separate from the test. You're right. It was
separate from the test, and you stick it through a machine called a Scantron, and it reads all your answers.
Yeah, the machine's the Scantron, I think.
Dude,
right?
every class I took in high school came with a Scantron, and that's how
every
test. So I took a lot of I took tests with these forms. I just didn't know what they were called or anything.
Yeah.
Right?
So
I think everybody, from our generation, everybody knows what a Scantron.
Yeah, well, that's why I think it's funny that they named the beer Scantron, because I was like, that's so funny. It's typical of this brewery, though. Like, it totally is the right time frame and everything.
Yeah.
That thing's funny. Anyway, go ahead, man. I just wanted to show you guys that. I thought that was funny.
Okay. So I have a matrix.
Yeah.
That has these nodes, which are all of the distribution centers from Target, and the distance in hours that I scraped from Google Maps using a different piece of code that I found actually.
So is that the weight or something?
No, this is just the number of the node and the name of the town.
No, yeah.
I'll show you
the hours is what I meant.
Oh, the hour. Oh, yeah. Okay.
Yeah. So I have. Let me.
Suffolk, Virginia. What the Okanoka?
So the hours, like John, the weight, they're gonna be on the edges.
So I have this.
Well, let's see what he made.
So I have this, and this is the time between the two locations.
So
You
so
notice
this is
1 and 1 and 0.
how come this is. Oh, wait. How come this is a 35? Oh, it's a 35. So this is an adjacency because this is
Yeah,
the
yeah,
rows and the columns are
yeah,
nodes, right?
yeah, yeah.
Yeah, well, what I was going to get into is I tried to write my own neural network, and when I was about halfway through programming my neural network, I realized that there's a faster way to represent this, which is with a dictionary.
Yeah, yeah, dude. This isn't you right. What you have there is an adjacency matrix, and the problem with an
Yeah, yeah.
adjacency matrix is if in a directed graph you're sort of doubling the work, right? So you could create an adjacency list, which is like probably what you're about to do, which you have a dictionary, you have node 1, and you have all the edges that node 1 points to. And then node 2.
Well, no, what I
Wait,
have is
that's the indice, or that's the
this is
other
a
matrix, right?
dictionary, and you have node from, node to,
Right.
in a tuple inside of it,
Right.
and then you have the edge value.
Right. You basically have an edge list. And you could do this exact thing in net what you're doing right there. And you basically
Yeah.
you're saying I'm going to create a list of edges. And you could load up that list of edges and it would build the graph for you in Network X. I actually do that a couple of times.
Exactly. And I realized halfway through programming my neural network that this was like the best way to do it.
What's
Wait,
funny about what you're saying
isn't that
is,
so this is
Go ahead. Sorry. Please.
this is the same information as like even if it's in a list.
It's
or,
all the
or
same.
it's an incidence matrix.
The only thing he
essentially,
doesn't
right?
have here is if he wanted to add properties to the nodes themselves. So now he has this thing called an edge value, which is really just a property. In this case, it could be a weight, whatever. But basically, if you think of like a graph, so a graph database is probably one of the best examples of what you can do to a graph because you have nodes, you have edges, and then you have properties that you can put on those nodes and on those edges. But most of the time, you're really just looking at nodes and their labels, like whatever they label them. So in this case, 1 through 34, and then you have an edge weight,
Yeah.
right? But that's not that. You can do a lot more than that. You can have just generically have properties on edges and properties on nodes. In the case that where he's loading up an edge list, you can't really do that.
Well, he would
Well,
create.
yeah, all you have to do is add a comma and then property too.
Well, you have to put a property to the node from, but the problem with what you're saying here is you're going to have.
You wouldn't have to because you have. This is drawing the line,
right?
So you know where it's from and where it's to,
right?
And then the thickness of the line, but you can have other properties of that line.
Yes, but that line 40 that you wrote there represents an edge, right? So you can do exactly what you're saying, like. You can replace edge value and property with a dictionary that has value, property, has anything you want on it, right? So you can
you can put another dictionary.
But what I'm saying is that you also have this concept of having properties on the nodes themselves, and you can't do that in this format because in your case, you're going to have multiple times where you have nodes from and to, where from is one node and to is another.
You can by creating a separate.
You have to do separately. Yeah. So
you create another dictionary.
Well, could it? Wait,
which is like node.
Right. No, that's exactly right.
Quick,
you'd have to do it separately, though. Is all I'm saying.
Node number and then like some properties.
You could also hold all that information in like a proper node structure as well.
This is how I was thinking you would do it. You're thinking like metadata.
Yeah.
Because if you had a bunch of documents,
well, I mean, it's literally what
properties,
like Neo4j
and stuff like that. You could go property.
Well, this is what you're doing now is literally what like Neo4j and graph databases like Tiger and all these databases. This is what they do. They give you a node. You have a node, and you can add properties to the node. And then when you write graph queries against the database, you match on the properties. And that's what makes it really crazy is that you can find shortest path and longest path through things based on only ones that have certain properties and stuff like that. It's kind of that. I mean, it's kind of amazing, actually.
Isn't that a similar concept to actually just create? I mean, you see people create node structures with certain, a node could have certain properties and certain relationship. Like it's like creating a node like class or something. Right? Isn't that
what was the name of that graphing program you had? I installed it.
Network X for Python or for what?
No, for Julia.
Oh, well, honestly, man, like anything that you explored is going to be deeper than I explored because only thing I found out
Okay.
was graph plot, and that seemed like a visualization thing. I mean, I was looking
Okay,
more
let me
for
look it up then. I want to look up the code example. I'm going to show you that there's an algorithm. So you're in the realm of like operations research, which is like what I'm really good at. And there's an algorithm. It starts with a D that you run to find the shortest path.
Dijkstra. You're talking about Dijkstra.
Yeah, that guy. Yeah.
Yeah, Dijkstra's algorithm is I mean, that's what Google Maps uses, or at least hybrid of Dijkstra's. Dijkstra's a popular. I mean, it's a popular. I think it's a breadth first search algorithm. The way it works, but basically, Shane, if you haven't, Dijkstra's algorithm.
Yeah, I've seen it, but
So
I don't.
Dijkstra. So if you think of a maze, right? If you think of like nothing to do with graph algorithms or anything, you just think of a maze, and basically Dijkstra's algorithm kind of tries to go down every path in the maze
Yeah.
until it.
Okay.
And then
I mean, I'm
so
familiar with like breadth first and depth first.
What was the
approach.
name of?
Dijkstra is Dijkstra. So I'm sure that's what you're talking
No.
about.
I just want to show you the code example. What is the
Oh,
name?
light
of the
graphs. I
package?
haven't seen
'Cause
that. That's cool.
Lightgraph is one of the .jl files from it, but I'm trying to look
Uh-huh.
up what the name of the.
Yeah.
Let me just look up network graphs. I use Start Page, by the way.
What's that? Oh, start page. What's that?
It's like an anonymous search engine.
I've been using Brave browser.
Hmm.
Brave browser even has like so if you know Michael, are you on Signal? You use Signal?
Yeah, I use Signal.
Yeah. So Brave browser has so the one thing I would criticize Signal for, and it's not really their fault, it's just that it feels like it's harder to send media across the wire.
Yeah.
So, and you can understand why. You're like, oh, it's totally encrypted end to end, so it's got to deal with this nonsense.
Here it is. So I'm going to bookmark this.
Brave has a video conferencing software that does the same thing. But I imagine, I'm going to guess that it's pretty slow.
So Lightgraphs is the main package from Julia Graphs, and
Julia Graphs is a package. I'll have to check that out. Okay.
Yeah.
Oh yeah, I see it up there. Okay. Oh yeah.
It says that that breadth first search is just Dijkstra algorithm, but all edge weights equal to 1.
Right.
Okay.
Yeah,
Cool.
and I think you can't have negative edge weights as well.
Here we go.
Well, you said
So this is from Simple Weighted Graph, and you see they just add the edge. So they specified a simple weighted graph with 3 nodes, and they added the edges. And then when they search it, they use Dijkstra, shortest path.
Yeah, sure. But wait. So add edge. So the thing about Julia is the exclamation point is mutating the currently existing thing, which most of the time people don't ever think about, but that's what it is doing. But then, but then it has So it says add edge. So I'm guessing it's saying add an edge from 1 to 2 that has a weight of
that is 0.5. Yeah.
0.5. And it's just interesting that it's finding the shortest path with Dijkstra because of what Shane just read. Is that the Dijkstra's weights are all the same?
No. BFS is Dijkstra with all the weights being
Got it. Okay,
other
yeah.
way
That
around,
makes
yeah.
sense. That makes more sense.
So Dijkstra probably came like maybe first or something. It's like the superset of BFS.
No. Breadth first would come first, and then Dijkstra would add weights into the situation. So that's why Google Maps uses.
It's generalized is what I was going for with that. It's a generalized version of BFS, right?
Right. Oh, I see why you're saying. Okay,
No, Dijkstra doesn't add weights. We already have weights.
No. It
okay.
considers the weights when is the point.
Yeah. It
yeah.
finds there's an alternative way to do that, which is using a solver. So you can do you know quadratic programming or linear programming?
I have no idea. No, I never. Heard
No.
Okay, so linear programming, you have like a bunch of distances between locations, and you want to find the fastest pathway through that. So what you do is you plug random numbers in, and it comes to the solution of the system of linear equations.
Huh. Interesting.
And that's actually how you
interesting.
do it. But this Dijkstra is like an alternative way of doing that.
Well,
And I didn't even hear this. Until
so
I started
Dijkstra's
getting
very honestly, Dijkstra's a very, very common. Like it's not like it's worth. I don't know if the book's gonna do it, but it's very much worth coding your own Dijkstra algorithm because it's not that complicated. Like a lot of these graph algorithms.
Yeah,
are,
I tried to before. I've tried to do that with the network.
A lot of these graph algorithms are very iterative, not that complicated at all, but easy to mess up, right? Easy to mess up, and that's why they're named after people and what they didn't just come out 100 years ago. Is because, it's just like because you have to consider, have I seen this node before? Have I not? That kind of stuff. But oh, that's weird. But basically, like they're very, very much worth writing your own thing and making sure you get it right. Like just like a breadth first search would be, just like a depth first search would be. Dijkstra is an example of that. All these algorithms, like in my Shane, this all comes from that algorithms.
But the alternative is. So this is going to search through the network in a systematic way.
Very,
but
very,
the alternative
very,
is
very
use a solver.
deterministic and iterative, right? Very much so.
Yeah. Whereas it sounded like the approach that you presented was random and like.
Well, it's not random. There's many different types of solvers. There's nonlinear solvers.
No.
There's linear solvers.
Yeah, no, it's
no.
not the linear.
There's evolutionary
it's not random.
algorithm.
It's not random. He included random elements to it.
Yeah, that's.
But it's not in and of itself is not random. Like Shane, there was an example. I think I forget what it was that you and I were talking about.
Okay.
And it does so by
real quick. So it sounded
binary value to the use of each node, and then it's going to alternate those binary values and minimize the distance. So basically, in linear programming and quadratic programming, you have something called the objective function. And the objective function with this algorithm is min distance.
Right.
And you set up a system of linear equations to express the constraints on the system.
Yeah,
I would have to see what the system of linear equations looks like. I can understand how.
Let me see if I can find
it's
a
basically
linear.
The solution of the system of linear equations. But
I do this a lot. This is like super useful.
Right. It's just that
example.
what I'm trying to say is like things like Dijkstra and breadth first search. They're so having nothing to do with calculus. Having nothing. They're very like Legos. They're like basic building block. There's no conceptually like super duper
here's your objective function. And here's your constraints. So, like, they're set up as constraints, really.
Sure. Okay. Sure. Absolutely. So you have you have a bunch of piecewise constraints.
So you can have constraints like I can't go from location A to location B. I just can't do that.
Right.
And you can have a constraint that becomes a constraint.
So it's set up as this piecewise function.
Your constraints amount to a domain, and you're basically saying find the max within this domain. So
max, min.
Yeah, whatever.
Whatever you want.
Yeah.
Whatever you want, really. Yeah. No. Yeah. Actually, what's kind of amazing about this?
I mean, like this is like a special case. So like using this algorithm only solves for the minimum by searching through the nodes in a possibly inefficient manner, but using many different types of solvers, like an evolutionary solver or something like that, you can solve the same system faster.
I would be impressed if this stuff could beat Dijkstra's algorithm. I would be
It's lightning fast.
I would be impressed mostly because I'm also aware that like Google Maps uses Dijkstra's stuff, so like they don't exactly.
They might have to, yeah.
But that's what I'm saying. Like I would be very impressed if you can beat some of these very fundamental algorithms, like a breadth first search. Like you could beat it with something else. There's probably with a certain bound in which you can beat it at, depending on certain criteria. But I'm absolutely interested because I want to see it beat it. Quite frankly, I don't care how
this is
complex
the
it is.
other textbook that I was considering doing. Like,
Oh, cool.
There's network
Cool.
there's network optimization right here.
Oh,
There's
nice,
network
dude. No, I didn't even know about you. Wait, did you share this? I didn't know about this.
Yeah, this is the other one that I was saying we should do.
Oh my god, I had no idea. Absolutely,
This
we
is
should do
with
this.
Julia.
Yeah, I'm absolutely down.
Yeah.
So after we get through this,
Yeah.
by the way,
But all of this I know how to do, or like I'm very good at like
good.
this type of.
So just
they call it operations research.
just to put things, yeah. Actually, my buddy from Brown, I was talking to him. I was like, "What the hell are you talking?" I was like, "What is your major?" And he said, "I want to look through the text just so I could tell you." But basically, he's like you. Like he worked. So this dude worked for like Shane. I think you know him. Let me see if I can pull him up. He worked for like Morgan Stanley, and he basically made like a crap load of money, and now he just doesn't do anything. He's like my age. But
I've made like systems with this strategy. This is like how to solve like many different types of problems.
yeah.
Not just that simple use case of the.
But what I'm getting at is I asked him. I was like, what is your mate? Because I know he's a math guy, right? Like, but now he just like farms and does stuff like that because he can. And I was just like, what do you, and he said something about operations research, and I was just like, I don't even know what that really is. And he started talking to me the same way that you're kind of speaking now. I'm gonna pull it up.
Yeah.
In a moment.
It's that. It
I
sounds.
just like took to this stuff because it was like just made sense to me.
So what's on the radar for the? Oh, Shane, you want to say something? Sorry, go ahead.
Well, no, I was just gonna say it sounded like I don't know if this is related. And you can correct me, Michael, if I'm wrong. But you're talking about how like there's like evolutionary like models or networks that can like approximate this kind of stuff. And
Oh my
something I
God.
learned.
He
learn,
literally
like-
wrote operations research in our text message. He,
And-
no. I think it's crazy because I think it's so
Yeah,
funny
that's
that you're talking. You and him, like you would have like a really interesting conversation. So.
Yeah, I'm like super good at this. I built this system.
He said
that,
I
like,
was
you
up.
can
Here's
only
what he
buy
said. Wait, let me
hour
just tell you.
blocks.
Sorry, let me just tell you what he said, and then
Yeah.
you can say whatever. I was applied math, heavy in pros stats and operations theory. I said, what's operations theory? He goes, basically applying analytical methods to make management decisions. It's used in finance, business, manufacturing, called operations research as well. So that's what he said to me.
Similar. It's the same topic. Engineers do this too. They do industrial engineering, which is a lot of this stuff.
That's so funny, man. I'm totally going to point him
It's
to
so
our
useful.
stream.
You could do this in Excel and solve these network problems
No,
like
thanks.
lightning fast.
I have so many problems with Excel, Michael, that I have. It's like it's sort of like you know, almost punching me in the balls as you're telling me to try to use this product.
Yeah.
I have not. I just can't even. My brain is like
Yeah.
feels that punch at the same time, and I'm just like, no thanks. But yeah, okay, I got you.
So let's see if we can. Okay, so it talks about it here too. That algorithm.
Yeah. So I mean, I don't know if it's complete. You know, obviously, like neural nets can approximate any function, and Dijkstra has it does this specific thing, right? And
Yeah, it does a specific thing.
and that's like
deterministic.
that's why a neural net is a neural net, right? I think it's called like universal like approximation.
Dijkstra's deterministic, man. It's very
Yeah. But if you
iterative.
if you ask someone that knew nothing about graph theory to traverse like a graph and come up with like an algorithm for it, like they would to John's point that these are like building blocks, they would come up with like BFS or DFS, right? It's a very like natural.
The way I think about a neural network is it's just like a shit ton of linear regressions.
Right. I think that's kind of what Shane's talking about.
Like it's kind of a weird way to think about it, but it really.
I mean,
is.
if you haven't heard it, you can wiki.
And it's folding the error, the error on itself.
They can literally approximate any function, right? It's called universal approximation.
Universal
theorem.
approximation. Yeah.
Yeah, exactly. So it's a very generalized, and
So
maybe lightning fast.
What's on our radar, guys? Just to get a heads up, is so Michael. I didn't know about this book. I don't know if you posted it. I didn't see it. Whatever it is, this is awesome. But there's okay, so just on our radar, right? Like at least from my perspective, and as it relates to Julia. So we're in the middle of this linear algebra book. That's one. There's another book that is a Julia statistics book. Then there's this book that you just found, which is a network book in Julia. I'm imagining as we're going through these things are going to blow up.
It's not a network book. It's specifically operations research, I believe.
Okay. So it's an operations research book. And then there's one other thing, and it's this thing that Shane and I started called GEN, and it's probabilistic programming, and it's very, very interesting. I think, Michael, you would really like this because it's
we'd love to. Yeah.
The closest thing that I've ever that I know of is like PyTorch, right? So it's like PyTorch. It's like this. It's a very interesting thing because you just it's like you know how Julia does vectorized operations. Imagine just passing it like random distributions all the time, and it's like this really interesting way of looking at programming and stuff like that. I think so. Anyway, so we have three things. We have the statistics one. We have this operations research book, and we have GEN. And GEN gets into the AI, by the way. The probabilistic programming gets into this whole AI approach. Yeah. So I feel like we should try to do all of them. I don't see why not. Just keep going. So we'll finish our book now, but we have this other two at the same time. So statistics, I almost think we should do GEN maybe last, but maybe not. I mean, so I don't know what you guys want to do. We can make a decision later, but just to throw all those on your radar right now, you know, where we go from there. So,
yeah.
Do you guys want to get going?
Well, I will tell you,
this
is super powerful. You could use this with tons of stuff.
Yeah, like, I mean, can you share this?
Once you learn how to do this, you can't unlearn how to do this. This is like, I use linear programming and like quadratic programming and like they call them different things, but it doesn't really matter.
Can you share this in our chat, please? Because
I'll share.
I'm gonna share this with my buddy. Shane, maybe you can pull up.
This is like a really
I'm gonna share my screen.
Research book, but I have better ones. I have like 5 operations research books.
Right, except this one applies to the programming language Julia.
So, this applies to Julia.
Yeah. And you'll have a lot to offer in that supplemental. So you know, cool. Thanks.
All right.
You guys ready to move on to do a little bit?
Yeah. So I think.
So I just wanted to.
No, that's great, man.
I wanted to show you guys that stuff and how I thought about the problem.
Yeah.
So we could have it like clearly like laid out, like, you know, where we're going and what we need to do, I guess.
For sure.
Yeah, absolutely. And I'm gonna do some research this weekend because I'd never even heard of linear programming or quadratic programming. So I'm excited.
This is the basis. Like, you don't even need a programming language. You could just like write a mathematical programming language this way. So.
Yeah. Cool. Yeah, so I think
So I got this thing called Taro, and I got to figure out how to import Excel file.
Cool. All right. So I think we were at this concert. The flow conservation is where we ended. Very quick summary, at least. You know, I was lost for a while, but I think it started to click a bit at the end. The incidence difference between the incidence matrix and adjacency matrix, which we talked about briefly, but columns in an incidence matrix are edges, rows are nodes. In an adjacency matrix, columns and rows are nodes.
But there's other way, like Michael pointed out, there's other ways of representing an entire graph. You can literally represent the entire graph. If you disregard properties, you can literally represent the entire graph as an edge list. Or an adjacency list. There's a couple of different ways of doing it.
Yeah. Awesome. Yep. And I think one other thing John pointed out was, you know, there might be like a computational benefit to not representing it as an adjacency matrix.
Well, that's what he was saying. Or like
you lose.
As well. Right.
Yeah.
Let me start a new.
Okay. So flow conservation. So I guess we're on sources now. Okay. in many applications, it is useful to include additional flows called source flows that enter, leave the network at the nodes, not along the edges. We denote these flows with an n vector. We can think of S as a flow that enters the network. Oh, okay, not from the edge. So up here, which we didn't get to this, we didn't read this, but we see all the S's here. So these are the source flows.
Yeah, I pointed that out last time.
Oh, okay, cool. I missed that.
Yeah.
Flow conservation with sources. The equation AX plus S equals 0 means that the flow is conserved at each node, counting the source flow. The total of all incoming flow from the incoming edges. And how do you say that? Exogenous source? Oh, exogenous source minus the total outgoing flow from the outgoing edges. And the exogenous sinks is 0. Sorry, total of all incoming flow from the incoming edges and exogenous minus the okay, is 0. Yeah. As an example, flow conservation with sources can be used as an approximate model of a power grid, with X being the vector of power flows along the transmission lines. Okay, cool. SI greater than 0 representing a generator injecting power into the grid, so that's our source. And SI less than 0 representing a load that consumes power at node I. Okay, cool. Representing a substation where power is exchanged among transmission lines with no generation or load attached. Okay. For the example above, consider the source vector 1, 0, negative 1, 0, which corresponds to an injection of a unit of flow into node 1 and the removal of 1 unit of flow at node 3. Yep. Okay.
Yeah.
So there's a source.
Okay, cool. So node 3 is sync.
It sounds like a source is the opposite of a sink. Which I think.
Yes.
It's like a faucet.
The source is the opposite
source.
of the sink. Okay.
Yeah. Yep. Exactly. Flow is conserved at nodes 2 and 4. For this source, the flow vector satisfies the flow conservation.
It's pretty cool.
And okay. Yeah, it's great. That's great. And it totally makes sense too that the source has an impact on this.
See, that's an interesting flow vector because, like, I don't know, how do you come up with that? You know, it's almost like you have to solve some system equation to figure this out. You know what I'm saying? Like,
so A here is still the A from above, right?
Yeah, I mean, the A is that diagram that you have right there.
Yeah,
right?
Yeah. This is
so like that's not going to change, but yeah, like what you do to see. What's interesting about the one you just showed. Yeah, so that one will come to 0, but the one you just showed right here. Oh, okay. I thought they were all positive. I was going to say that would be really interesting. So the fourth and can you go back to that diagram? The fourth and the fifth are negative.
Yeah.
So that means the fourth and the fifth points in opposite direction. Every other one is the way it is. So
but the fourth points in the same direction, though, right? It's still this clockwise.
It was negative.
Oh. Yeah, but it's not immediately obvious, is what I'm saying. That the fourth and the fifth would be negative just from looking at the diagram, right?
No.
Yeah, you'd have to.
The vector.
You'd have to be able to.
The vector shows them as negative.
Yeah.
The vector that you gave. So that diagram. Yeah. Okay, so that diagram
is A. I understand that.
So
the diagram is not the way I would draw it.
but when you multiply it by that vector, or when you try to look at the circulation, you can flip edge 4 and edge 5 to point from 1 to 3 and 4 to 3, and then you have the representation scaled by the weights that vector is talking about. So 0.6, 0.3, 0.6, negative 0.1, whatever. But I would say negate them, so to point the heads in the other direction, and then talk about how much flow is on them. Then you can talk about the weight on the thing. But so I'm trying to understand.
Negate positive weights.
What?
Like if you negated the direction, right?
If the vector you gave it is negative, I think it's going It's going to point in the opposite direction of what it's pointing at. I think that makes sense, right? And the amount. So in the case of the x vector that you see below this, they literally point in the opposite directions, but they maintain the exact same flow, right? Like because right in the one that you gave us next, they do or don't point in the opposite directions, but there's a different weight on the flow.
Yeah.
The flow is a little bit different.
Yeah.
It's less, actually, in fact.
Yeah.
So that's the point, is like you need to multiply it by that matrix to find out exactly how much is going in and out of each node to show if it has conservation or not.
Yeah.
I just trying to visualize looking at this diagram. If I flip both those arrows back and back, if I can see how it could have a conservation of energy. And can you go back up for a second? Just for a moment, right here. So if you flip those two edge 4 and edge 5s, can you imagine?
Well, that's what I was trying to say before. I said it's not immediately obvious, even
Right.
from trying to imagine in your head. At least it's not obvious to me.
No,
Because
it's
it's
not.
flowing out into S4, right?
Like John just said, if we flip 4 and 5, I mean, you have to keep in mind the
It
sources
seems like it gets
too, I
stuck
guess.
at 3. It seems like it would get stuck at 3.
So keep in mind that
Well,
source
it's
1.
just simple math. Like once you add it all together.
Yeah, doing it out is simple math for sure. The visualization, I think we have to keep in mind what the sources are too, right?
Oh, yes, you're right. That's how, because I was saying it goes into 3, and 3 is a -1. That's why.
So 3 is negative 1.
Yeah. That's
then-
the only reason that
okay.
works out, because I was like kind of really confused. So wait, where's the source in this? What's the source vector? Can we look at the source vector?
Yeah, it's right. It's 1 0 negative
Okay,
1 0.
so node 1 is the source. So forget about all the other S's, right? So if you imagine node 3 flipping the arrow to point to S3. So the one that comes out of node 3, that black arrow, flip it to point to S3. Also flip edge 4 and edge 5. And erase.
So this is where the
erase
operations
S4
and
research
H5.
constraints comes into play, because you might have a constraint that says 1, 2, 3, and 4 cannot be less than 0. Right?
What?
And then that forces this whole thing to equalize.
You know what?
So, like,
it's actually,
you see how they have, like, you can have a balance
it's
in 1, 2, 3, and 4 that's
simple, by
less
the
than
way.
0.
It's super simple, by the way. It's very, very easy, actually. Point everything to node 3. Right? So 1 goes to 4 goes to 3, 1 goes to 3, 1 goes to 2 goes to 3, right?
Yeah.
Everyone agree?
Yeah.
So that's the only thing.
Yeah.
So it comes in at S1 with a flow of 1, and it leaves at S3 with a flow of -1.
It leaves at S3 negative 1.
So everything
Okay,
goes
has
to
to.
S. Right, exactly. So you don't even need to think of the little details of it. It's just the fact that that's so my argument would almost be based on that source. I guess if the flow doesn't constrain itself, that most you would just need to adjust what's in node 1 and node 3.
Yeah.
And you could probably come out with a 0 flow based on that.
Yeah.
That's
I mean,
interesting.
you could imagine larger networks where there's like some circulation in the bottom right corner that kind of it still outflows to S3, but then it could also maybe get trapped in like some circulation.
That's I think what the point of this. Yeah, exactly. I think that's the point of the flow vector. Because you can see how much is actually flowing in and out of these, or flowing through these edges, right? You can see it's almost like electricity is probably like a good example, because you can see the ampage or whatever it is. I'm not a good person like that, but you could probably understand how much voltage maybe is going through each wire or conductor or whatever it is.
Yeah.
So it's the same thing.
Sure,
I'm totally understanding this. Like, by the way, I'm like
cool.
Yeah, but go down to the flows.
Go down. You want to see the?
Yeah. So this is where you're gonna. No. Well, that's the source, right? The source makes sense, right? As long as the
sources,
the source.
Oh, you want
makes
the flow
sense.
vector?
Well,
I just want to see the S.
Right. The source makes sense. Yeah. Show them the S. That makes sense. That's actually the most important thing, honestly.
This is the
right
S,
here.
right?
Yeah. Yep. He just wants to see it.
Yeah.
So it comes into 1 and it leaves at 3. And my point was the fact that everything was pointing to 3 implies that yes, it does matter what the flow vector was in terms of the actual numbers, but the truth behind the whole thing is if it's all coming into node 1 and it's all leaving at node 3,
Yeah.
if
It
that's
does-
even
yeah.
possible based on the source.
It doesn't matter
code.
how much there is.
So
Well,
imagine
I don't
this is
know.
a
I would like to
production
see
line.
that. It probably
Why
matters.
is that S3 arrow? Like I think their graph is just inaccurate.
What do you
Because
mean? Go
if this was a production line, you're leaving out S3.
Yeah, that's why it's
so
a negative
why
1.
is the arrow pointing inward?
Because this
You know
is
what I mean?
yes, I do. Because this is the natural state of the matrix, right?
Yeah, this-
However, the source vector changes that state, just like the
Yeah.
other vector
Yeah.
does. So the source vector of a 1 means that S1 exists in the way that it
Oh,
already
yeah.
is.
Yeah.
Having a 0 means S2 does not
No.
even exist.
Yeah,
Having a
yeah,
negative
yeah, yeah.
1 means S3 exists, but its direction is in the opposite
this-
of what it
Yeah.
Yeah.
and then
Just
the same
flip
thing-
this arrow right here.
So their diagram
Okay,
is
so I
not
guess
wrong.
Get rid of
this
those.
diagram does make some sense.
It
Well, the
does.
diagram
It's
can't
just
be
it's
wrong.
awkward because you have to flip these things. You have like this is the insight
Yeah.
that I had yesterday when I realized that first of all they were talking about edges and nodes, but then it was like, well, the negative numbers just mean whatever you see here is the opposite.
Yeah.
That's
Flipping
all
the
it
direction.
means.
Yeah.
It doesn't mean anything.
Yeah, the graph itself can't be wrong. Like John said, this is the initial state of the graph, and it
Right.
exists how it does. The only way it would be wrong is if they got like the incidence
Yes.
matrix wrong or something, which they didn't, right? So now we're talking about this like
all they implied in the
yeah.
graph.
where the intake is.
Yeah,
you know?
all they implied in the graph that they didn't imply was that there were sources and that every node had a source pointing
Yes.
toward it.
Yes.
So that, but that's
yes.
not. I can understand that. I don't think that's crazy. Like,
Well, they were setting us up for this as
Okay.
well. I would
All
imagine.
right, that all makes sense. Let's
But
go down
yeah,
to-
I think John's I think if it's negative, flipping it in your head kind of makes all of this make sense. You flip the third one right here, and then for the last two, you flip the last two.
and then
and
you
then-
realize
Yeah,
all
but
the
if you were
arrows
doing
point
a
to
present-
three.
presentation.
They all
If
point
you're
to
doing a
three.
presentation for someone, you would want to.
You'd
wanna
wanna show them kind of
yeah,
flipping
you'd
or
want to show
something.
it. Like just
Yeah.
writing a
not
source
even-
vector doesn't
Like
really.
that's what
yeah,
I'm
yeah,
saying.
yeah.
It's kind of like
Yeah.
Yeah, it doesn't. paint
it's like
it.
you have natural state, and then you have like what it's actually doing.
Yeah. But it's not even just going to 3; it's going to S3
No,
specifically.
I agree.
Kind of,
I agree
right?
with
It's that
Michael.
out-
If
Yeah,
this was
it
3
is.
blue, 1
It's
brown,
exiting
he would have
through
shown
S3.
it. Let's put it that
That's
way.
what I was about to say. That he would have an animation. That
He would
flips
have it
the arrow.
flipping
It's-
and weaving.
Yeah,
and,
yeah, yeah.
Like, yeah.
Well, he would show each one by one.
Yeah,
Right?
He
Like,
would.
so
You're
when
right.
he'd
You're
show
right.
the
That's
first-
exactly
yeah,
how he
and
would.
then he
Yeah,
would-
yeah, yeah.
And then when negative one came in, it would flip around.
Shout out to 3
Like,
blue, 1 brown.
Yeah.
yeah. Ridiculous guy, man.
Yeah.
Okay, great.
But this has other uses. Like the reason why you get into operations research with this stuff is okay. You have shipping, you have transportation, but you also have production lines and stuff like that. So a
Yeah.
lot of industrial engineers work with factories
Mm.
and stuff like that. So like I'm thinking of this small little graph as a production line.
Yeah. Yeah. Wait. So, what would be for a production line? What the nodes are like people or something? Or they're like certain
They're like phases in the
phases in the production? Oh.
yeah, certain things that need to occur in
Yeah.
a certain order. And the thing is, there are certain things that can occur simultaneously.
Yeah.
Well, I mean, no
As
one's
well.
saying that
Yeah,
you
that's fine.
can't have like multiple edges coming out and pointing to the same node, right? Because then you have 2 pieces of
Yeah.
traffic coming out, and like I totally get what you're saying. Like there could be basically
Yeah.
parallel execution.
Yeah.
I mean, it makes sense. Like I think
Yeah.
this is a very simplistic, version.
Yeah, I mean, I don't even-
but I know that you guys will get promoted if I teach you linear. like if I teach you optimization, like you'll get promoted.
Yeah.
You get promoted. I didn't hear that the first time you
No,
said
no,
it.
that's why I laughed. Yeah.
You get
No,
promoted.
I think he's not totally wrong though, because I mean
you use it with everything.
Right, well,
I use
exactly.
it like all the time.
and it gets into like sort of just this generalized idea of project management and stuff like that, which is really the way in our company how you progress. So I don't think you're
Yeah.
wrong. I just think it's funny.
Oh,
that you
when you
said
get
that.
into those, I even know there's even algorithms for project management that go on their own.
Oh, yeah. I feel like
I've written them.
that feels like to me like a subdomain of like game theory or something. Like you were saying, operations, like
Research.
like well, not yeah, but you had another, not just operations. You said like operations, like management or something like that.
Yeah, operations research, operations management.
Oh, well, I think
There's
my buddy said
industrial
operation
engineering,
theory.
and they all do the same thing.
Oh yeah, yeah. Your buddy, I think I was talking. It almost gets into like game theory. It sounds
It's
like
called
I don't
operation
know.
theory.
Yeah.
Yeah.
So game theory is
Yeah.
Cool.
game theory is more like, based on my utility or whatever, based on my
Yeah.
whatever matters to me.
Yeah,
What's
a
the
set of
decision I'm going to make.
rules.
In their case, it's like
a set of
literally
rules,
a bunch of steps. So
Like,
they're
like
not.
here's one example of an algorithm
Okay.
that comes from that. So say I have people and they work shifts, and they all have different blocks of time that they can work, and they have constraints around when they can work. You can automatically optimize all of that.
So for
it's
example,
all about
Michael,
these like optimizations using different
so,
algorithms.
Michael, if
Like,
you wanted to write a scheduler, right, like for your employees,
I've done that before.
right? So what you're saying is this is the field that you would sort of utilize to do that.
Yes.
Yeah, I mean that makes sense to
Yeah,
me.
that's interesting.
In
Yeah.
fact, Galil and I were trying to write an app that really helped restaurants with this.
Or
So it seems
inventory.
like
Inventory also,
Sure,
like-
sure.
How do you know when to reorder inventory?
You know what? You're making me think I should get my buddy.
There's a mathematical
involved in
answer
this.
to that question.
Right. I get it. I believe it.
And that algorithm is kind of interesting because it involves some statistical variation. So it does involve like z-scores or a t-score rather.
Shane, how much do we have left in this section? Because I know
We got to do these convolutions. Let's
Yeah.
go through the convolutions.
wait, but we're not even up to that. We're in the derelict.
Oh, okay.
Hold on. Wait, Shane, how much do we have left before we get to convolutions? I mean, I could do convolutions.
We have a two page and a half, 2 pages.
How long is
page and a half.
convolutions? We might have to save convolutions. I hate to say it, but
Well, we kind of like achieved what we wanted. Like John and I were talking before this, and we just wanted to like talk and like go through some stuff today.
so maybe if
No, man,
if,
this is good
if
for
we can
me.
get up to if
for
we can
sure.
get up to convolutions right now, I think I would be very happy. So
Yeah,
And I can give
No.
an outline of the two different methods for convolution.
all right, let's get to
After.
convolutions. Let's get
Okay.
there,
Yeah.
and then you do that, and then we'll call it, and then
Okay.
we can
No,
meet again.
I'm very happy going through this slowly because this has been it is all good, but it's definitely been
it's
harder
valuable.
for
It's
me
not.
than the rest. Yeah,
If you've never seen
Yeah.
any of this stuff before, or even if you have, it's just one of those things that you should.
yeah,
talk about.
exactly.
Yeah.
Exactly. All right, so node potentials. A graph is also useful when we focus on the values of some quantity at each graph vertex or node. Let V be an n vector, often interpreted as a potential, where Vi is the potential value at node I. We can give simple interpretation in a matrix vector. Product U equals A transpose V. The M vector U equals A transpose V gives the potential differences across the edges. So you have Uj equals VL minus VK,
What does that mean?
where edge J goes from node
I
K
think
to node
it's
L.
the difference between the inflow and the outflow, but I can't really
V
fully
Graph is also useful when focusing on
interprets
values
as
of some
potential.
quantity.
They're calling it potential.
right.
Oh, they're just talking about the alternative way of viewing it. So like each node has a balance, right? And that balance can't. I mean, it shouldn't be
Right,
negative.
that's what I'm saying.
Mhm.
Like each,
Yeah.
like I don't know, but so if you take Uj or some part of U and you say V, what is it, Vi and Vk? What is Vi? Is Vi? Yeah, what is V? First of all, V is an n vector interpreted.
Well,
as
V is a
potential.
potential.
So you're
This,
yeah, so like I don't really know what that means, honestly. So it's like
V
by
being
by
yeah.
definition, V.
So
is
actually, what
potential.
it's thinking of, right? You got to think physics with what it's talking about right now, because it's saying that the node has a certain capacity.
Hmm.
So I think capacity is probably a more appropriate.
Okay.
Okay,
explanation.
sure.
Yeah.
Okay. So it's just an attribute or like magnitude of a specific node, right? Every node has a potential value. Is that a
Yeah.
correct way of
A
thinking about it?
capacity.
A
It's
capacity, how much? Sure. It's a very important attribute to this node.
yeah.
Um,
What is derelict energy?
so then you can create this U vector that is the differences between every single node.
Yeah.
Or not every node, every adjacent node. Because it's
Yeah.
UL minus or VL minus VK.
It's across
Or
all
no.
edges. It
Oh,
looks like.
oh, yeah, all edges. Yeah, all edges. So you get okay. So you have this U vector that is the
It's all yeah. It's
difference
going to be a U vector of edges
of every node.
of edges. U is going to be edges.
Yeah, yeah.
It's the
Yep.
potential.
But
of
it's
the,
not. So I guess. Yeah. Okay. So yeah. It's not like so instead of the edge having like a weight like we've been talking about, the edge has this potential, which is the difference
So
of the two nodes it
it
connects.
seems like it's transforming from node potentials to edge potentials.
Yeah. It's thinking like I'm thinking like water.
Yeah.
And like if the balance in node A is higher than in node B, then it can transfer at a certain rate through the edge.
I don't know if I would call it unless did they say node potential?
Well,
Because
look at the topic, the biggest.
oh
word.
no,
Node potential. Yeah.
no, node potential, yeah, but not edge potential, right?
Well, no,
So
but
it's like
the only reason
potential energy.
the only reason I say edge potential is says because the M vector U, whatever, gives the potential differences across the edges.
Yeah, that's fine.
UJ,
So it
where
represents
edge
an
J
edge.
goes from
Yeah.
node. Okay, so U is a vector of edges, is what I'm trying
Yes.
to say.
Yes. U is a vector of edges, but it's the vector of the
Edge potentials or whatever.
Yeah, sure. I like that. And edge potential is just the difference of the two potentials for the nodes.
For the nodes, right? Which isn't
Okay.
shouldn't be too surprising because
No, yeah. So that's actually that's and I like the I don't know. I like the capacity way of
sure,
what
definitely.
you're saying too. Okay.
Okay.
Dirichlet energy. When the M vector A transpose V is small.
Is this Dirac? No, is it?
Uh,
No, it's not.
Yeah.
What is V?
When the M vector, ATV is small, I think it's the potential from above. Right?
Is it U?
Oh, the guy's name was.
Okay.
No,
Dirichlet.
U is the potential differences. V is the potential.
Okay.
So when you have M vector ATV is small, it means that the potential differences across the edges are small. That totally makes sense.
Okay.
Another way, if you had like all the potentials were like 0.1 and 0.2, the difference between them is just going to be 0.1.
Yeah.
Right. Okay. Another way to say this is that the potentials of connected vertices are near each other. Okay. Quantitative measure of this is the function V given by.
Well, that kind of
dV.
makes sense. The potentials are near
It's
each
the
other.
norm.
Potentials
Yeah.
are near each other.
Right. That means that they're not spread out.
Yeah. Yep. So this function arises in many applications, and it's called the Dirichlet energy, associated
Or
with the graph,
Laplacian quadratic form.
Laplacian quadratic form. It can be expressed as dV, which equals the summation of all the potential differences squared.
So it's just the summation. Wait a minute. So is it? It's the summation of that U vector.
It's the summation of all the
but
u's
it's not.
squared,
It's not.
right?
Yeah, U squared. Right.
It's the summation of u squared. Oh,
So
yeah,
is it the
summation.
dot product of U dot U?
Yeah, right. Yeah, it is. Yeah, right.
I think so.
Yeah, you're right. You're right.
Yeah. This is hard.
Cool.
It's hard to visualize without having like a really.
I think it's U dot U.
Well, maybe I think they probably give us. Oh no, yeah, John. I'm pretty sure you're right. U dot U or U
Okay.
times U transpose, or
Same thing.
yeah, which is sum of squares of the potential differences of V across all the edges. The Dirichlet energy is small when the potential differences across the edges of the graph are small. Nodes that are connected by edges have similar potential values. Dirichlet energy is used as a measure non-smoothness or roughness. A set of node potentials on a graph, a set of node potentials with a small Dirichlet energy can be thought of as a smoothly varying across the graph. Thought of as smoothly varying across. Okay. Conversely, a set of potentials with large Dirichlet energy can be thought of as a non-smooth or rough. Okay, hold on. So
if it's large,
small is smooth and
right,
large is
So
rough.
if it's small, it implies that all the potential energy edges, like the potential energies from one node to another, are
Are
not
similar.
they're
Close.
right. They're similar because the difference between them is very, very small. Right.
Yeah.
That implies
We're
that
in physics right now.
No, I know. So the difference between them is very, very small. In other words, they're similar or whatever, right? So
yeah, it's the difference between not having a lot of energy and having a lot of energy to release.
Well, no, but it's not just that. It's the whole point is that the entire system itself has a similar amount of capacity, as you put it. Right, each node has a similar amount of capacity. The moment you take a capacity, so if I took a system that had 5 nodes in it, and I had all of them have like 100 billion volts, and I had one of them only has a capacity of 1 volt, you're going to have a problem because you're going to have a situation where one of them has a far lower capacity, so the Dirichlet energy that results of it is going to be rough, so to speak. Right, because
it's going to explode.
Well, in practical sense, it's going to explode. But you're going to have two situations where the edge differences, right, are going to be great. They're going to be very big, right?
Yeah.
And then if you square that, it's even worse, obviously, right? So if you're in a situation where they're all pretty much there's some homogeneity of it.
Homogeneous versus heterogeneous. Yeah.
Right. If there's homogeneity of the system, then the Dirichlet energy is going to be low, right?
Mm.
Does that make sense?
Yeah.
I feel like that makes sense.
Yeah. It makes perfect sense.
If you had one node that had really, really, really high potential and it was only connected to, and you imagine a graph where all the potential,
that's like the opposite of what I just said. Actually, that's funny.
But imagine all the nodes are very small potential, and then you have one that has high potential and it's only connected to one other one. Then the energy of the whole system is going to be about the same as that one node as well.
That's a good point. That's a great way to look at it, actually, because the difference between them is going to be a lot closer to it than it is to the other of the other ones. So all the edges are going to be a lot closer to it.
Yeah. But now imagine that one node with a lot of potential has 2 edges. Then it's actually the energy of the whole system is going to be 2 times the potential of that node about. And then it's going to be the number of edges it has times the potential of that node or something. It's interesting. This is an interesting visual.
I think capacity is different from potential energy. Capacity is like a limit. Potential energy is like, this example is sort of like you have an atom and it's in motion and it's going to hit these other atoms and it carrying a certain amount of potential energy and it can transfer. So it's like a different type of problem than capacity. Capacity is like it can produce at a certain maximum rate.
That's what I was thinking of, honestly, was capacity.
Yeah.
We're in the realm of physics. This is a physics example.
Yeah, I mean, but I'm not sure the difference on what you said. Like, I think your capacity analogy was very good, actually. I feel like
capacity is like I have pipes and they can only withstand a certain amount of pressure.
Yeah, that's what I was thinking. That's exactly what I was thinking.
Yeah, or I have like transistors and they can only withstand a certain amount of
voltage or
capacity at each point in the network. And if they cannot exceed that. It's a hard limit.
Yeah.
So I guess this potential energy is like it's potential to be transferred.
Yeah.
You know, like transfer of energy.
There's no hard limit is kind of what you're like. With capacity, you have this concept of a hard limit that a node can't go above.
It can't exceed.
But here, there's no limit.
Potential energy is something to be dispersed.
Yeah.
And what this graph is measuring is like how much potential energy there is in the whole system to be dispersed, and the smoothness of that line based on the equality within. But why is that graph? Can you scroll down to that graph, the chain graph?
Wait, can we just read the sentence above if it
Okay,
relates? Okay. As a simple example, consider the potential vector v 1, -1, 2, -1 for the graph shown in figure 7.2.
Can you scroll
For
to
this
sorry, can you scroll to 7.2 real quick? 1,
Oh
1,
yeah,
2,
yeah, yeah,
negative
yeah, yeah.
1.
Which one's?
I think that's
Where's
the
that?
original. That's the one we've been looking at the whole time. Yeah, that maybe. Well, that one, but I think the other one is the same. Yeah, I think
That's it.
it's the same. No, keep going. You're good. You keep going. Right there.
Oh,
It's the same graph. It's the same graph.
Oh yeah, yeah.
Right,
It's just
right.
with
So they're
sources.
saying 1, 1. What is it? 2, -1, or -2,
Yeah,
1 or something.
Yeah, something.
So it's probably the nodes, right? All right, so let's go there. We know the graph. We have that in our heads. Let's move on. Let's go to what it says.
Okay, 1, -1, 2, -1.
Okay.
For
So
each.
node 1, just picture the graph in your heads where node 3,
Yeah.
node 3 basically points to node 1 and 4.
Oh,
1,
yes,
2, 3, 4,
yeah.
right? Okay. Fine. So that's node 1.
that
So
has
it has a
that has that
potential. These
potential.
got to be nodes, right?
Yeah, this is for each node. V is for the nodes.
Yeah.
This is the potential at each node.
So the potentials
like-
at
yeah.
each edge because
So
of
maybe it really is capacity.
So
well,
the potential.
hold on. Yeah, that's what I'm trying to say. So now that we can look at the potentials of each edge are based on the
Yeah.
potentials of the differences between each node.
Yeah.
And
2,
so for example,
3.
so what is the first edge? Edge 1 was 1 to 2, right?
So you have a U or a edge potential of 2, right? 1 and -1.
Right. So I think you get -1 minus 1. So you get -2.
-2.
Yeah, exactly. And then from 2 to 3, same kind of idea.
You get 3.
No. Wait, what is this?
Yeah, 2 minus -1, right?
So if we look at so node 3 has a no. Node 3, so node 2 has a -1 at it. Node
Yeah.
3 has a 2, right?
Yes.
So we want to find the difference between them. So and they're pointing from 2 to 3. So we get a 2 minus a, yeah, so I'm kind of confused.
You get 2 minus -1, 3, right? For the edge potential.
Oh, so that's where the 3 comes from.
Yeah, it's just the difference between all of these.
Where was edge 2, by the way? I think I mixed up what edge.
3 is the difference between -2. I mean between
No,
2
I think
and
I think we're good. I think the edges I got mixed up. Where can you scroll up to the? I'm sorry. Can you scroll up to that diagram real quick?
Yeah,
Where's
yeah.
edge 2? Oh, that's why.
Edge 2.
I thought edge 2 was going from 2 to 3. That's the problem. So you're right. Edge 3 was a 3 from 2 to 3. So edge 2 goes from 1 to 4.
So 1 to 4.
Yeah.
What do we have down here? So then you have -1 minus 1, right? -2.
Yes, exactly.
Yeah.
Cool.
Exactly,
Okay.
exactly.
Okay. Yeah, I like
It's like another use case.
I like calling you edge potentials. I think that's a good way of, instead of just the differences of, it's the same thing, but
Oh yeah, I mean, I think.
But what is this
easy-
graph
easy-
of
easy to
that's
visualize.
down here?
okay.
Well, let's get there.
Wait, hold on one sec.
We
So
want to get
this set of potentials, the potential differences across the edges are relatively large.
Yes.
Okay, so they actually did it all out for us.
and it becomes 27 when you do that.
Yeah,
whole,
you get
you
27.
basically square them all and you add them. So you get 4,
And then
4,
now-
4, 4, 9, 1, 9.
Yeah.
So 9
But
and
in this
9 are
case-
18. The 2 4s make an 8, so that's 26 plus 1 is 27.
So then, but for the second example, these are obviously a lot more, a lot closer. So then you get an Dirichlet energy of 3, which is so much smaller, obviously.
Right. So then the idea would be is if you looked at the graph. So I guess you can probably scroll down now. Yeah.
So what are they changing? What is K?
It's not this thing. It's what? Yeah. What is going on with this figure? What is
All right,
this
well,
figure?
we haven't
Chain
gotten up to
graph.
7.4, so let's keep.
Oh,
reading.
it's not. We're probably not going to hit it for a while.
Oh, right. Chain graph is right here. Do we want to talk about this more, or we want to go to chain graph?
Let's
I
go
mean,
to chain graph.
Yeah, let's talk about go to chain
Okay.
graph and then let's finish that
Okay.
conversation. So chain graph has
So,
7.4 and 7.5 in it.
okay. So incidence graph and the Dirichlet energy function have particularly simple form for the chain graph shown in 7.4 with n vertices and matrix D described in 119.
This is basically use.
The Dirichlet energy is this.
Yeah.
Yep. So that's fun. The sum of squares of the differences we knew between consecutive entries. Yep. This is used as a measure of non-smoothness of vector v, considered as a time series. Okay. So now the edges are between.
Series.
So now the edges are between
So
n
all
to
you're
n plus 1,
all you're doing is showing
making a time
each,
series.
What is the flow throughout time?
Yeah, you're
Yeah,
showing
yeah,
each of those
yeah.
edges over time.
Yeah,
Like, because the edge
yeah.
has a limit on how much.
So
can
in this
flow
case, it's
through
two
it.
vectors of length 100 with an overall. So like if you took the overall, I guess, sum of all those things, you'd get
Yeah.
1.14, and then the second, what's dB? What's B? Oh, the second.
So say you
second
measure
graph.
the derelict energy at every second.
Oh, you mean? Oh, yeah. You're measuring it at every unit of time.
What's
I
the
guess
difference
it's a second
between
here.
those two graphs?
So one's smooth and one's rough, right? But what are they? Well, I'm guessing here. I
Oh,
have no
that's
idea.
the difference.
No, I'm guessing.
No,
I'm
I think
guessing,
you're
but it looks-
right, but that's wow. Okay. So what? Wow. So on the one on the left, the difference between basically any of those nodes is very very small. So it's almost
Yeah.
like it's talking about like kind of like the slope almost between any two nodes in a weird way.
It's just something about the smoothness and the roughness of the line.
Yeah.
Yeah.
I don't know enough about
Yeah.
smoothness and roughness itself, but it seems yeah.
Well,
like-
rough is just a large energy, is how they defined it, and then smooth is a small energy. But I'm a little confused. So, what exactly is the difference between B and A? Like, I understand that one of them, but they don't actually give us a B or an A.
No. It is though. Like if you think of so look at the very first node of both of those graphs, right?
Yeah,
And then look at the second node of both of those graphs.
yeah,
So the first node like is in graph B, it's jagged.
yeah,
So it's got a high Dirichlet energy.
yes.
Now, even if you drew a line that like through all of those points,
Yeah.
right? That's not what they're talking about. They're talking about from one node to another. There's
Yeah,
like,
yeah.
There's a lot of
There's
like
so
difference
there's
in
low-
energy.
Yeah.
You know what I mean?
Yep. Yeah.
And it's
It's very and that's
So
why
what-
like smooth and rough didn't make a lot of sense to me before, but now looking at these two
Well,
graphs, like,
now
that was the reason why I
And
wanted
it-
to scroll down to the graph.
it's
'cause
very
it
much
makes sense.
yeah, it's very much apparent. Can we talk about the overall pattern of the whole thing as well, and what exactly that
yeah, that's a
means?
good question. Actually, that's a really good question. Like why is it in this I think it Shane, I think it might be arbitrary. I'm going to say that. I think that
Okay.
they might have it might just be simply based on the node potentials.
Yeah.
You know what I mean? Like I feel
Yeah.
like
I
because
yeah.
K's node potential, right? Like so you have nodes labeled 1 to 100. And the pattern between this is a chain graph, right? So the pattern
Yeah.
only goes from one node to its subsequent node.
Yes.
So can you scroll up for a second, or maybe not scroll up, scroll down. I'm sorry. The incidence matrix and the Dirichlet function have a particularly simple form for the chain graph.
Yeah.
Shown. I don't know how you come up with a chain graph exactly.
Well, it sounds like it's a time series. Like it's just the time series in a graph.
It's the
format.
derelict energy over time, I guess.
Well,
It's-
I guess one thing, at least this is how I'm thinking about it, and if I'm wrong, you guys can correct me. But this is the exact same stuff this is the exact same thing that we're doing up here. The only difference is the graph has changed.
That's what I'm
because we
saying.
have a
That's
time
what I'm saying.
series
That's
now.
what I'm saying. You have one node points to its subsequent node only. It's
Yes.
it's a
Yeah.
unidirectional from
Yes.
the succession from
Yeah.
the first one all the
But-
way to the last,
yeah.
all the way to the last in order.
Yeah.
And,
And
the
see how they
Because it's a
1,
time
2,
series, you get that kind
3,
of graph.
0, 1, 2, 3.
and they're showing the exact same chain graph. Okay, so what they're trying to show you is the exact same graph for both of them with two different Dirichlet energies.
Yes. Yes.
That's all they're
yes.
saying. The difference between
Yeah.
the difference between 1 and 2 on graph B is big,
It's-
and the difference
mm.
between
It's yeah.
even
It's
though
small.
the overall flow ends up being the same. The
Yeah.
graph B chain graph has a far bigger
Yeah.
Dirichlet energy than the first one, than A.
So,
I think that's all
yeah.
they're really saying.
Yeah. I mean, they're just showing us the difference between a rough and a smooth system, and we can visualize it now, even though, like
the
you said,
reason
the
you're
energy
saying
is the same.
the reason you're saying
the whole
time
time.
series, if you took any time series situation, right, any time series situation, and you found the differences between one element and the element that came after
Yeah.
preceding elements, and they were
Yeah.
tiny, and you added them up,
Yeah.
that would be your Dirichlet energy. Or you
Yeah,
squared
yeah,
them.
yeah.
If you squared them,
Yeah.
that'd be your Dirichlet energy. And if
I mean, yeah.
you know what I mean?
Yeah. I was just gonna say, like, I don't really think of like putting a time series like in a graph, structure. Like, but it
But
it just
clearly,
goes to show
clearly,
that-
that's what it's doing, right? Like
yeah. that's what I'm saying.
the
It just
thing
goes
about
to show
graphs
how,
is they can really represent anything.
how
so-
generalized graphs
Well-
are.
Well,
yeah.
imagine you could use a neural network for a time series too.
Yeah, but the time series is really just one event happens and then the next event happens. It's
Yeah.
very simple. It's a one
Yeah,
node.
it's y
points to the
regressed
next
against
node.
time
Yeah, it's a very simple graph.
against
really, actually.
n 1, 2, 3, or in this case 1, 2, 3, 4.
Right, like today's value of the stock can only imply tomorrow's value. There's no other
Yep.
like it has to, you know what I
Yep.
mean? It has to progress in this order. It can't go from today to 4 days
Yeah.
from now, then back to tomorrow. And it has to go in this very specific like one node, the next node, the next node. Right, so I don't know what they mean by the incidence matrix, Dirichlet energy, and function have a particularly simpler form for the chain graph.
Yeah.
I mean, okay. They're saying given a chain
There's
graph,
an equation right there.
right? But they're saying given a chain graph, like the chain graph is given. So they're saying in a
Yeah.
time series situation that's given, you do this, right? They're not
Yeah.
saying everything we've seen before can be reduced to a chain graph. They're not saying that. They're just saying that if you look at a chain graph, like it's very simple if you look at a chain graph. So they're just literally saying one not even a unary tree, a unary tree, a unary directed tree. If you look at that,
Yeah.
which is basically a time series, then this is what you can get. This. And you look at- They're just trying to show you. They're trying to get rid of everything else and just show you the difference between Dirichlet energies.
Yeah.
Yes, it's a
Yeah.
diagnostic.
Yeah, exactly. If you looked at a graph that said like the energy at each point, I mean, we already all know this, but just to express it, this would obviously be like a graph of everything very, very, very close to zero. This one would, jump around a bit more, a higher difference.
Yeah.
If this wasn't a chain graph, I don't even know how you would plot it, really.
Yeah.
Because you'd have a
Yeah,
node pointing to multiple things. In this case, one node only points to the next node, so you're just looking at the differences between one node and the next node.
Yeah,
And
I guess
that's
it's
what
not a
they're-
diagnostic because you can't.
That's all
really
their
use
graphing
it.
is. They're graphing the edges.
Yeah.
Well, they're graphing the node, the value. They're graphing the edges, basically. They're graphing
Yeah.
the nodes themselves. But if you look at the lines between the nodes on
Yeah,
diagram
those
B,
are
that's the edge
Yeah,
difference.
those are the edges. But then they
Yeah,
also
yeah.
tell us the overall energy, and it's very
Well,
easy
the
to see
overall
that.
energy is squaring
Adding
all
all
of those,
these-
squaring
yeah,
all
yeah.
of them, all
And
those
then-
Yeah,
edge,
exactly.
all those edge lengths or all those lines, and then adding them up.
Yeah, sum of squares. For
All right, I'll
exactly.
share
Okay,
screen
great.
for let me do convolution.
Well, yeah. Can you just briefly go over it? Because I
Yeah, I
pretty
just wanna
much have
draw
to
something.
stop at in like.
Yeah, I'm
5
gonna go.
minutes.
I'm gonna go for a run too. But it'd be good to get an overview. for
Let's
now.
do an overview. I gotta
Screen.
stop in like 5 minutes, so let's do it.
Oh, I'm on the wrong screen. Hold on. Okay, so I'm just gonna draw in Excel. So imagine a regular neural network. So a regular neural network is you're going to have like an input layer that is like this, and then you're going to have hidden layers, right? And then you're going to have an output layer, which is like, I don't know, something like that, right? So this is your neural network. So with a convolution, you have any image processing, you have an image that is a certain number of pixels by a certain number of pixels, right? This is your input, and you may have, say, you're trying to recognize an object within this input. This is your picture. So in order to train the algorithm to recognize the object, you have to have a picture of the object, which is like this, and you got to move it around. So you move it around, and that's called a convolution. So when I move this square around the image, and I also rotate it and stuff like that, each time I move it is a convolution.
That's interesting. Okay.
So this is why they're called. You just taught me this. This is why they're called convolutional neural nets. With inputs of images,
because they have a square input. They have like a rectangular or a square input. Yeah, and every time you move that around,
great.
They're called convolutional neural networks because you keep moving it around and rotating it. There's an alternative way to do it, which is like, this is your input. This is your input, and it's flowing into it flows into a smaller image, so you're down sampling it, right? And you move this thing around, so you have different.
Wait, pause for 1 second. Why do I know the term downsampling? Didn't that come up in the book?
We went over.
Yeah.
We just went over it in the book.
We went over it. Yeah.
Okay.
But this is the main one. This is the main way to do convolutions.
That's awesome. I feel like I understand.
Dude, that's great,
a little bit.
Yeah, that was.
So you have your neural network right here.
You just connected some serious.
But it's great for this chapter because they're talking about rotations.
Way too into the math on like these things, and you got to think of like simple examples. That's the simplest way.
I'm all about that. I think this is really good because just to summarize a lot of what you just said as far as my interpretation goes. So you have this sort of square, right? So like you think of this as a matrix. This matrix can get rotated, it can get reflected, or whatever. It can get translated to different places or whatever, and have multiple sort of types of things, movements, or whatever the word is for rotations, translations, reflections. Yeah. So convolutions, right? So it does that around the image.
Say it's a picture of a banana, and I'm trying to teach it to detect the object of a banana.
Well, it's a picture of a lot of things.
I want the banana to be displayed within the picture in many different rotated forms.
Well, it's a picture of a lot of things, but you have a banana in it or whatever.
Yeah, exactly.
Yeah. Right.
But the alternative way to do it is to show it a bunch of pictures with people holding bananas. And the thing is, okay, dog and cat is the easiest example. So, like, say I'm showing it pictures of dogs, and I'm showing it pictures of cats. But what happens if I have a picture of a dog and a cat, which is the reason why you need to train it by moving the object around.
Right.
Not by moving this larger square around the smaller square. That's the other way that you could do it.
Oh, so you're saying you have you could take the smaller square and move it around the larger square, but you can take the larger square and move it around the smaller square until it matches up on that.
Those are the two different ways to train convolutional neural networks.
Interesting.
But there must be a name for the two different training.
I don't think they really get into it because I've probably looked at this way more than they have. But I noticed that MIT was doing it differently on one example than IBM was doing it on another example. I took two.
Oh, so but they don't there's not a common name. Like there's not.
No.
Okay.
Like anything, there's probably is, but I think Michael's point is not really.
Doesn't really matter. Yeah.
Yeah.
The point is you just sort of pick what works, what you're building toward, and then,
It's actually a really simple.
I like it. I like it a lot. It's very clear. It's
Sure.
a nice little thing you did.
Whereas if you traditional neural network,
Yeah, nice visual.
yeah, if you had
Yeah.
a traditional neural network, you would have X1 X's really. Just a straight line of data.
Yeah.
Well, this is kind of what we're probably more,
one-dimensional.
like you
here's
said,
your Y.
used to. Right. How neural nets work.
This is what a multi-factor model. A multi-factor model would look like this. You'd have Y as your output, and X1, X2, X3. And they did originally, before they came out with convolutional neural networks, they did originally try to train it with a traditional neural network, but it didn't really work that well.
Right.
So you'll see there are examples. Let me pull up Mintz.
That's the
Harrison.
handwriting thing.
So they try it with different. Yeah, Minst is like one of them. Okay, so here's the comparison of many different types of models. Here's using clustering, boosted stumps.
Oh my god.
There's a vector machine, a traditional neural network, which has 2 hidden layers, 3 hidden layers, and then eventually they invented the convolutional neural network where I can input instead of stacking the vectors. So like instead of breaking this thing down into these stacked vectors,
Yeah.
like that, and just like
Yeah.
breaking all the lines down into stacked vectors, they input a whole square.
Yeah. So that's actually relevant to kind of what we've seen in Julia as well, right? Like one long array or an array of arrays.
Yeah.
Hey
So,
guys, I'm gonna turn the
it turns
stream
out
off.
that these convolutional neural networks work really well.
I'm gonna turn the stream off.
Like
Okay,
look at the difference in accuracy. So here's